In Prolog, all data and also programs are represented as terms. Terms are defined inductively. Each term is either a variable, an atomic term, or a compound term. A variable starts with an uppercase letter or with an underscore. A single underscore denotes an anonymous variable, which is a variable that is different from all other variables and other anonymous variables that occur in the program. For example, x, y, and Prolog are variables. In Prolog, a variable is truly a variable and stands for anything at all. There are different kinds of atomic terms. The most common ones are atoms and integers. Some Prolog systems also support other atomic terms, such as rational numbers, complex numbers, and so on. Examples of atoms are a, at, and atom. This is the most common form of atoms, a sequence of letters and digits starting with a lowercase letter. If you want to use an atom that doesn't follow this pattern, you can put it in single quotes. For example, Prolog in single quotes is an atom. Examples of integers are 12, 100, and 2020. Floating point numbers are also atomic terms. A compound term consists of a functor name f and n arguments. N is called the arity of the term. Each argument is again a term. A functor is a functor name together with an arity. f/n is called the principal functor of the term. Our first example of a compound term is f of a. Its functor name is f and its arity is 1, so this is a term with principal functor f1. The term's single argument is the atom A. We can visualize the structure of a term as an ordered tree. Variables and atomic terms are leaves. A compound term can be drawn as an inner node whose children are the term's arguments. As another example, let us consider compound terms with 2 and 3 arguments, f of a b and f of a b c. In the cases so far, all arguments are atoms. Let us turn one of these arguments into another compound term, say f of a b g of c, or f of a b g of c and d. These are more deeply nested compound terms. Here is another example. In this case, one of the subterms is a variable. Terms are so expressive that you can represent every data structure with them. For example, we can use terms to represent arithmetic expressions, such as the sum of 1 and 2, or the product of 3 and the sum of 1 and 2. Terms come into existence by simply writing them down. There is no need to declare anything. Note also that we haven't yet attached any meaning to these terms. We will later see how we can evaluate integer expressions using the predicate #equals. As another example, we can use terms to represent full binary trees. In such trees, there are two kinds of nodes, leaves and inner nodes, which have exactly two children. Let us use leaf of L to represent a leaf with attached data L. And let us use terms of the form node of left and right to represent an inner node and its two children, left and right. With these building blocks, we can represent a concrete full binary tree. Some terms can be written in several different ways. For example, here is a term in infix notation. And here is a term in list notation. In both cases, the syntax tree shows the term's abstract structure. We will later consider such notational variants in more detail. The key point for now is that no matter how you write these things, they are all terms, and they all fall into the categories of terms we have discussed.